Before we can really grasp the calculus involved in curve sketching, we must have a solid understanding of functions and their definitions. Of course, we can graph many different equations that don't all represent functions, but by investigating the rules that define what a function is, we will gain a much deeper understanding of why aspects of calculus work, such as limits of functions, tangents, gradients, and differentiation. Firstly, any curve that we sketch can be defined as a relation, since a relation is simply a relationship between two variables. For example, a relationship between two variables could be something like y is always the inverse of its corresponding x value. We can write this relationship as an algebraic rule, as we know that an inverse means a fraction, and this would give us that y is equal to 1 over x. The algebraic rule that defines their relationship is the equation that we're trying to sketch, so in our case, our sketch results in a hyperbola. But while every curve is a relation, not every curve is a function. A function is a special kind of relation whereby every single x value on the curve is unique, and therefore no x value occurs twice. For example, the set of ordered pairs 1, 1, 2, 2, 3, 3, and 4, 4 is a function as there are no repeated x values. However, if we added another coordinate, say 1 minus 1, this set is no longer classified as a function, as the x value x equals 1 now contains two corresponding y values, y equals 1 and y equals minus 1, so x is no longer unique. We can test if a relation is a function very quickly by either observing the coordinates to ensure that no x value is used twice, or by sketching the curve and drawing a vertical line through it. Since a function only uses any x value once, a vertical line will only cut it in one place. If it cuts it more than once, then the x value has been used more than once, and so it's not a function. If we are working with a function, then we can replace the y values on our axis with the notation f of x, meaning the function's value for each unique x value. It's often useful to think of a function like a machine that will output a unique y value for any x value that's put into it. Mathematically, this means that for every x value we substitute into the equation of a function, we obtain only one y value. Looking at the equation in the example, we know that 2x squared minus x plus 3 gives us a basic parabola. And by observing a quick sketch, we can see that this parabola will pass the vertical line test, and so therefore we are working with a function. The notation used here in our example is asking us to find the function's value when x is equal to -1 and the function's value when x is equal to x plus h. By inputting our given x values into our equation, we will obtain the unique y value that matches it in its coordinate. So, when x is equal to -1, the function's value is equal to 2 times -1 squared minus -1 plus 3. Which upon evaluation gives us +6. And so we'll have the unique coordinate -1, 6 in our graph. Similarly, the function's value when x is equal to x plus h gives us 2 outside of x plus h squared minus x plus h plus 3. Since our x value in this particular example is algebraic, then our corresponding y value will also be algebraic. And so now we are just simply required to expand the expression given and simplify it as much as possible. So working from left to right, we would have 2x squared plus 4xh plus 2h squared minus x minus h plus 3. There are no like terms in this expression, and so therefore it cannot be simplified further. The purpose of looking at functions is to assist us with graphing any given relation. And so it's now important to have a look at some of the properties of a function. Firstly, the domain and the range of our function. We know that the domain is defined as the set of all possible x values, and that the range is therefore the corresponding set of all the possible y values. These two concepts link in with the limit of a function and also a function's continuity, meaning that if a function is discontinuous or has a gap in it, then it will have a limiting x value. But if a function is continuous, then it will have a domain of all real x, as there is no limit to the x values possible. It is also useful to consider the symmetry of our function. So if a function can be defined as either even or odd, then it will be symmetrical about a certain point. An even function is symmetrical about the y-axis, and it's defined by substituting a negative value of x and obtaining the original function. If a function is odd, then it's symmetrical about the line y equals x, and so it appears to be symmetrical about the origin. It is defined by substituting a negative value of x and obtaining the opposite function to the original, or the negative version of it. Once we've observed the nature of our function, we can then find its critical values to help us accurately sketch the curve. So we can find the roots or x-intercepts of our equation by either factorising or substituting y equals 0 into the equation. We can find any y-intercepts of our equation by substituting x equals 0 into our equation to find the point where it crosses the y-axis. We can find any turning points of our equation, and we know that these are commonly referred to as stationary points. And then by observing what happens at the end points of our graph, so as x is heading to negative infinity and as x is heading to positive infinity. Finally, let's have a look at an example of how all of this fits together. So we're given the function x cubed minus 4x. The first thing we're asked to do is to show that the function is odd. As the question is asking us to show something, we must write down all relevant mathematical steps. And as we just saw, to show that a function is odd, we need to substitute a negative value of x into our function and obtain the negative version of the equation. So our solution is to start by substituting negative x for every x value in the equation. So we'll have negative x cubed minus 4 times negative x. We then need to expand this and simplify it as much as possible. The first term will result in negative x cubed, as 3 negatives multiplied together give us back a negative. And the second term, the 2 negatives result in a positive 4x. If we now factorise the negative out of this expression, we will obtain negative out the front of x cubed, and we'll need another negative inside the brackets to obtain that positive. So we'll get negative 4x. Looking at the expression we now have, this gives us back the negative version of our original function, which is exactly the definition of an odd function. And so we have proven the function is odd. The second part of the question asks us to define the domain and the range of the function. This is most easily done by considering the function's continuity and whether it would have any limits. By considering the function's equation, there are no x values that when substituted into this equation will result in the equation not working. And so therefore every x value is valid. This leads us to a domain of all real x, which we write as x belongs to the real numbers. For the range of our function, this is most easily found by observing what happens at the end points of our graph, or as x is heading to positive and negative infinity, as this will tell us whether there are any minimum or maximum values that our curve achieves. For our equation, as we substitute very large negative values into our function heads towards very large negative values. And so there is no minimum or maximum value here. Similarly, as we substitute very large values of x into our function, then we result in very large y values. And so again, there's no minimum or maximum value. So the range gives us back all real y, or y also belongs to the real numbers. Thirdly, we're asked to show that the function has x-intercepts, meaning that the y value at this point is equal to 0, of -2, 0, and 2. So again, that word show means that we have to have all relevant mathematical steps in our solution. And we're going to start by substituting in y equals 0. So we'll make the statement that x-intercepts occur when y equals 0 and make that substitution. The next thing we need to do is factorise our expression. So everything has a factor of x, which we'll take out the front, and we're left with x squared minus 4, which we know factorises to the difference of two squares. So that gives us x outside of x minus 2 and x plus 2. And by making each factor equal to 0, we obtain our x-intercepts. X equals 0, x equals positive 2, and x equals negative 2. Lastly, we're asked to sketch the function. And the last thing that would be useful to know here is our y-intercept. Our y-intercept is found by substituting in x equals 0. When we do that, everything in this function goes to 0. We have 0 cubed and minus 4 times 0. And so our y-intercept gives us back 0 as well. And so from all of this information, we can now sketch an accurate representation of this function. Our function is odd, and so it is symmetrical about the line y equals x. And so we can see that what is happening on one side of that line is mirrored on the other side. Our function continues in both directions for all real x and all real y, as identified with the domain and the range. We have our x-intercepts of -2, 0, and 2, which also happens to be our corresponding y-intercept. And the last thing that we will identify when we study the calculus topic is how to find the coordinates of these stationary points. But for now, the information that we've observed in the functions topic is enough to draw an accurate sketch.